So good morning. Welcome to Krishna's classroom. Let us continue with our discussions on inner product spaces. We have already looked at linear functionals and their representations. Now we look at a more general class of linear maps, namely linear transformations. We keep ourselves to finite dimensional inner product spaces. So with some changes, sometimes very substantial, you can push across the theory to more general inner product spaces or even Banach spaces and so on. That we shall not bother at the moment. So we assume X and Y are of dimension n and m respectively. We look at linear maps from X to Y. So let T be it is linear in the following sense, that T of, that is, we have T of alpha 1 x1 plus alpha 2 x2 tx2, where x1, x2 belong to x, and obviously tx1, tx2 belong to, and alpha 1, alpha 2 C, or it can be so you have now the space of all linear transformations from X to Y. Let transformations and as we have seen in the case of vector spaces, Lxy is a vector space of dimension look at it, it's a vector space. I am not claiming anything about the inner product on this, okay. Right? Now, what I am interested in is this. You recall in the case of linear transformations on vector spaces or from one vector space into another, you had the dual spaces. Here also you have the dual space that we have already analyzed. And then on the dual space there is a dual operator. For a given t, there is a t prime. Okay? But of course there is some slight difference that you have here, because the the collection of all linear functionals have a conjugate linear structure, unlike in the case of general vector spaces where we did not have the inner product representing the linear function. Okay, so we were seeking representation with reference to the inner product that you have on the space. Okay, so let us work on that. Now, in the place of dual operator, so there is t from x to y, then you have x star and y star. So it induces a certain transformation from y star to x star, as you had in the case of dual operator, and t you had from x to y, t prime from y prime to x prime, okay, just dual operator. So just the same sort of idea that you are working, but now you are working from on x star and y star. Okay, so it is actually the set of all linear functionals with the induced inner product, and you can identify that x star with x with the inner product being flipped. Okay, so we have discussed it earlier. So let us explore this problem. So suppose you start with a t belonging to now what you have is this. So you can define, let us look at the picture, some diagram help you to work this. Then you have got y star and x star. Now you see that you can find a vector y belonging to x which maps the vector tx to some scalar. It's a linear map. Okay, this is a linear function. So this defines a linear function. So let me write this. This is equal to this is txy. Okay, so it's a scalar. So this belongs to C. Now what do you have? You see, this is a linear functional on X. Okay. So look at, so define now. This is of course the inner product that you have on Y. So let me just write. And on X there may be another inner product. Okay. Then you see that phi is a linear that is quite easy to see. You check whether phi of alpha 1 x1 plus alpha 2 x2 equal to alpha 1 times phi of x1 plus alpha 2 times phi of x2. The linearity of T is used. Okay. So that is done. Therefore, phi may be identified with a unique X star, Z belonging to X star, such that phi x equal to xz x. So this is again applying the representation theorem. Okay. So that means you have a vector here z which is uniquely determined, so that this is your x. So this carries x to this. This is the phi map, and this is now equal to x. So xz equal to, so tx so this associates with y a unique vector z. Okay, so that's what we have said. Therefore, it defines a map from, so this defines let us denote this by T star. Now what we want to prove is this. that is T star Y Z. Now what we claim is that T star is linear. So this is something which we would like to observe. So how do you prove this? You have to show that T star of T star of y1 plus y2, T star of alpha T star. Okay? So let us compute this. So T star of y1 equal to z1, T star of y2 equal to z2. Okay. So what is this T star of y1 plus y2? Okay, let's work on that. So see that how this association goes. You have got x this is equal to y2, and that now you can work on this and this. You immediately see that this is Tx y1 plus and which you see that this is equal to x so this is equal to And this is true for every x belonging to x, which in turn implies this is true if and only if now similarly let us work on this. So this is what we have to do. So this is the first part. Second part is to prove this one. X T star where alpha is a scalar. This is equal to Tx alpha y. This is true for every x, and this is equal to alpha conjugate, because in the inner product this is what happens. X Tx y, which is equal to alpha conjugate x which is equal to x alpha conjugate will go inside, it will become alpha right. And that is true for every x. Therefore, what do you get? So together these two, that is this part okay. So we proved both A and B, and therefore it is linear. So it's a linear transformation from y star to x star. So this is the direction, linear. Therefore T star it is uniquely defined. So there is a given T, there exists a uniquely defined linear transformation from y star to x star. Now this linear transformation is what you call the adjoint of T. Okay. So we give a name for this. So this is what you have. is called the adjoint of So what we have proved is that every linear transformation has a related transformation which you call the adjoint of the given linear transformation. Okay? And we are especially interested in this. We are often that means we are interested in what you call operators. Okay, so it is from x to x, and then it becomes from x star to x star. So you have got then t belonging to and of course it is defined by, it is connected by this here x dx so this is on the inner product of x. Okay, this is true for every x and y. So here what you have is this dx and d so this is what is called the adjoint operator. I mean, in this case, when the domain and range are the same space, we call it an operator. So corresponding to the linear operator D, there exists a uniquely defined adjoint operator, which you designate by D star. Okay, so we will be interested in this particular operator. Now what we want to do is just look at how a matrix representation looks like. And that's also interesting to see. Unlike in the case of a dual operator, we have seen that if D is represented by an m by n matrix, an n by m matrix, that is D is from, we are now not considering this, then this is n dimensional, this is m dimensional. Now you have seen that you can have a representation here Cm, you have a corresponding matrix which maps Cn to Cm, and there is a natural isomorphism or a isomorphism that you can set up by choosing an ordered basis. And we have seen that if you choose a basis x and a basis Y, then you have vectors in Cn and vectors in Cm, and you have a matrix T is a, so you write this as a column vector, say something like alpha 1, alpha 2, etc. alpha n. So you have got n rows here. So you have the operator is, so what you get is n rows, one column, and the operator that you have is this. It's an m by n operator. So you have an m by n matrix which maps a column vector with n rows to a column vector of m rows. Because you see that here you have a column vector of m rows, here you have a column vector of n rows. Now this is what you obtained. And then we have seen that the relation between T and T prime, suppose T is represented by Aij, T prime is represented by Bij, okay. Here it is a, then T prime is a n by m matrix, okay, where Bij is equal to Aji. That means the transpose of, that is the T prime matrix representation of T prime. Oh, of course, I think we are talking about the matrix representation of T prime. So what you have is, you have the dual basis, and what one has is this, that is Fi delta Ij. You know, these are the dual bases. So you are talking about the dual basis or the representation in terms of the dual basis for T prime, that is given by the matrix Bij, and in terms of dual basis, because it's a map from y prime to x prime. So you have a basis for y prime, you have basis for x prime, and with respect to that the representation is given by the matrix Bij, where Bij and Aij are related, and Bij is equal to Aji. Okay, or in other words, you get the interchange of columns and rows take place here. Okay, so let us see what happens in the case of T star. Is it the same as this? It will be something like this, but maybe there we have to be a bit cautious about this, because as I said, when you go to inner product spaces, you see that the corresponding map that you have would have a conjugation coming up. So let us work on that. Okay, let me just remove this. So let us explore this. First of all, you know that there exists an orthonormal basis for both x and y. And orthonormal for x, by which you mean xi such a basis, orthonormal basis exists. Let y. Now let me do one thing. Since we do not require this generality, this much of generality, but we will be often dealing with x equal to y, we shall take x equal to y consider the special case and we have the same then and then this is the orthonormal basis. So for y also you can choose the same orthonormal basis. Okay, one thing that you observe is that the dual basis x, because if you take this as f1, f2, etc., fn with the property that fi xi equal to fi xj equal to delta ij, then you see you have this fi, suppose this is the definition of fi, then you can show that this is equal to fi is represented by xi itself. So this is the, so that this is equal to 1 whenever I equal to j, otherwise it is 0. Therefore, you see that it's the same orthonormal basis which serves as a dual basis also. So that you can now start working on this. So we define T. Then we are going for the matrix representations with respect to this. Then T of xj equal to okay, T can be defined in this way. Okay. Then what do you have? Then the matrix representation for T is given by this gives the matrix representation for T. Okay, this we have seen the earlier how the matrix representation for a linear transformation from can be obtained once you have a basis chosen for both domain and range. Here the advantage that you have is that you are choosing the same basis for the both domain and range, because we are taking y equal to x. So this is what one has. Okay. And what you have is this. How is T star defined? T star is defined like this. X T star. Okay. This is the inner product that you have in X. So on both sides you have the inner product in X. Now you make the computation. So let us take X to be So let x be where psi 1, psi 2, psi n are the uniquely determined scalars. So this is the unique representation that you have. Okay? Why again these are all both uniquely determined. Now let us write down what Tx is. Because T is linear, Tx. Now we use this. Representation. Use for Txj. Therefore, substituting Xn for j equal to, this is what you get. So Tx becomes psi j Txj, which is equal to Txj is alpha ij psi. You can easily interchange the order of the summation and you get or in other words, the ith coordinate of Tx is going to be given by, or the ith coordinate of Tx is given by this one. Okay, this is the ith coordinate of Tx. Okay. Now what do we have? So we shall work with the operation of T star. Okay. So let us do the same thing for T star. We are going to connect that through the inner product. See this, you have an psi you have got here the matrix representation for T operating over psi equal to therefore, the matrix representation for T is given by psi I alpha ij, that is alpha ij. Now we shall do the same thing for Y. Okay, and we have the T star and how these are connected. Okay, suppose we take T star of equal to let me put a star here. Then what you have is that okay. See, you have okay, that's about the definition of T star. But Y is given by therefore Y is represented by the vector eta Cn. It becomes Rn if we are considering R. Okay. Now T star of xj equal to this. Therefore, you can get similarly T star of y. You can write by with eta 1, eta 2, etc. eta n, and this turns out to be sigma I j equal to 1 to n. alpha ij star therefore t star of y is represented by the column matrix or I can use the same terminology, the ith coordinate of eta j. That is the ith coordinate of that. Therefore, that gives the t star is represented by alpha ij star. So this is an n by n matrix. So this is what you get, the matrix representation. Okay. Or this working on eta. Therefore, this is the matrix representation for T. Now we are trying to find out, so how the matrix of T star. This is the central question. Now we work through what is called the inner product. So how T and T star are related? We know that T and T star are related through this is the relation. So we have to use this to get this. So we observe the following. X is represented by psi 1, psi 2, etc. psi n, and y is represented by eta 1, eta 2, etc. eta n. So Txy if you compute, this would turn out to be, because you are using the fact that xi, inner product of xi with xj is this is equal to, now you write down the two what is called the representations for this. Now that will give you, this is equal to, what is the representation for Tx? The representation for Tx is this. We have seen that Tx is represented by, the dot product of psi j. Xi and to be multiplied by sigma what is that? This is equal to eta 1, eta 2, etc. eta n. So eta you can write eta k xk or something like that to get this right. Okay, so if you work this out, what happens is when you, this will become multiplication by eta j conjugate, and xi xj will be delta ij, so you are taking the both for I and j the same, so you can write here k. Right. Therefore, if you work it out, this will become simply the inner product of, say, okay, for I equal to 1, so this will be eta I conjugate. Okay, so this is what it turns out to be. Right? Now, this is equal to, with alpha I j replaced by alpha I star. So it is going to be simply, yeah, psi I into sigma eta j. So you can actually compare the two and compare the coefficients of psi I eta j and psi I eta j on both sides. Okay. So what one gets in this, so comparing the two, so since we have the equality of these two. Okay, that means we have so you get eta j conjugate here, psi I here. So psi I eta j conjugate, you take the coefficient of the both. Okay, then you see that alpha ji conjugate. That means it's a transpose conjugate that comes. In the case of the dual operator, we had simply the transpose coming up. Now this is just, it's quite easy to verify this, because you can actually work on what is that, see, this is what we need is this has to happen for every psi I eta j. So you push the whole thing together and you write psi I eta j conjugate and look at the coefficient of that. Okay, and that should be true for every choice of psi I and eta j. That connects the alpha ij and alpha ij star, and this is the relation that you end up with. Okay, so it needs some little bit of work of writing down a few more steps and then making the computation. So I hope that you would do. The best way to do these kind of things is first you work on, say, something like n equal to 2. Okay, then it will be very clear how these things are coming up, and then generalize it for the general indices. So this is the proof of that. So you get alpha ij star is given by alpha ji conjugate. That means the T star, the matrix representation of T star is based on the orthonormal basis that you have chosen, is given by the matrix representation of T transpose conjugate. Okay, right? So you just change take the complex conjugate of the matrix for T, then transpose it, you will get the matrix representation for T star. This is the relation. See, you didn't have this complex conjugation coming there. This transpose was there in the case of the dual operator, but not here. This kind of relation will be reflected all through this case. Now we have earlier seen that there is the linearity and conjugate linearity coming into the picture. Okay? So similar things happen here. So it's the consequence of all that. Okay, I think that's a nice place to stop. So in the next lecture we will be looking at what are called self-adjoint linear transformations, unitary transformations. Okay. So they all, what you call, see, you look at the nature of the transformations and look at them as you do. See, I'll just give a hint. This is very important. So if you take a linear transformation from C1 to C1, one dimensional space. Now you see that Tz is going to be alpha z. So this alpha, with respect to some basis, this alpha will represent T. It's a scalar multiple. It's represented by scalar multiple. Okay. Then what about T star? T star is going to be equal to, is represented by alpha conjugate. Okay. So you see that in the complex plane, this corresponds to what is called the conjugate of the complex number alpha. Okay. If T is represented by alpha, then T star is represented by its complex conjugate. That's a relationship that you have. That is the special, because here there is no transposition, is not visible. So this is what you get. Okay. So if T is represented by alpha, then T star is represented by alpha conjugate. Okay. Now there are some special class of complex numbers which are important. What are they? They are that the real line is embedded in the complex plane. Okay. So the real numbers have a very special role to play. And in that case, what about, how do you characterize a real number? Alpha is a real number if and only if alpha conjugate is equal to alpha. Therefore, you see that the special case that I am talking about corresponds to alpha equal to alpha conjugate. Now, just pushing this idea across, you ask the following question. T okay, this is the transpose conjugate that you are taking. So this is the definition of what is called a self-adjoint operator. So if this property holds, what happens? You end up with what is called a self-adjoint operator, and that corresponds to the real line of the complex plane, because both the complex plane, if you take an alpha, this is alpha conjugate. So alpha equal to alpha conjugate if it is real. Then another interesting thing that is fascinating is the one of the unit circle. Here the property that you have is alpha conjugate equal to 1. This is the unit circle that you have. Okay? Consists of all those complex numbers for which alpha bar equal to alpha conjugate equal to 1. Now what is the corresponding thing that you have? You have got T, the matrix T multiplied with the matrix T star, matrix for T star with respect to the same basis that you have. This should be equal to the identity operator. Identity operator, this corresponds to alpha equal to 1. Identity operator. So you have to simply expect results of this kind. Identity operator. Or you say that T this class of operators that you look at, they are called the unitary operators. Okay? And if T equal to T star, then T is called self-adjoint, which corresponds to the real numbers. And I will make some more statements about this in my next lecture. So, thank you very much. But I suggest that you do all these computations. First do it for the case n equal to 2, and then push it up to the general case with the proper notations. I hope I have got the indices right. That you can check. If there is any mistake, you can always correct it. Thank you very much.